Welcome. Today's notes worksheet is entitled Quadratic Functions Day 1. The quadratic family is probably the most prevalent family to investigate at this particular level, and so we'll go ahead and take 3 days to go ahead and explore some algebraic characteristics of the quadratics and some applications of the quadratics. There's some great algebra that goes into this. So day 1 is very much the introduction, I guess. Day 2 is just more of the extension on the algebra, and in day 3 would primarily be working on some of the applications with the quadratics. So let's start it out. You probably have seen some of this before in your previous classes, so let's just kind of solidify some of these ideas and see where it's going to head. So anyway, let's go ahead and start. Number 1, it just says at the top of your page here, the standard form. We're going to actually take a look at 2 different forms of a quadratic function. So we'll start out today's lesson with the standard form, and basically it would be this. So f of x equals, and you've seen this before in terms of an equation in one variable. Now, of course, it is really a function in 2 variables, y in terms of x. So there's our ax squared plus bx plus c. So a quadratic is in the polynomials, and it is really a polynomial of degree 2, as you see right up there. So the squareds. I guess the only reason I have the or here is just, you know, f of x and y are really the same thing. So y in terms of x, that's really what it's going to play out to be. And we're going to take a look at that relationship, obviously, on the coordinate plane, and take a look at some of the algebraic characteristics that go with it. So let's take a peek. It says, when graphed on a coordinate plane, a quadratic function forms a parabola. We've seen this before, of course. So all different types of graphical patterns based on the family of functions, and the parabolas obviously come from the quadratics here. So I think we'll play around with this just a little bit. The only 2 types of parabolas that we're going to see over the next few days would be the parabolas that open up, and so that would be this piece right here, or the parabola that opens down, just like this. So you can explore and model parabolas opening to the left and right, also parabolas opening in a diagonal way. So I'm going to just draw a couple. So parabola opening to the right, a parabola opening to the left, a parabola opening kind of like this. But none of these that you see on the screen over here, none of these will pass the vertical line test. So these do not fit in the context of being a quadratic function. The only 2 types of parabolas that would be functions are these over here, the ones that open up and the ones that open down. These are the ones that pass the vertical line test. So those are the ones we'll take a look at. And we're going to, as I said, look at some of the characteristics that go behind that, and you know, again, kind of match the graph of the parabola to the equation in that form up there. So let's go for it. Number 1, and as a matter of fact, if you would please, can you put a big asterisk next to the vertex there? Really, most of the good algebra and I would argue most of the applications revolve around the concept of a vertex. So let's go ahead and fill in some of the blanks here and then see where the algebra leads us. So it says if the parabola opens up, and that would be this one right here, by the way, the vertex, which actually I'm going to go ahead and draw right there, there's the vertex, is really the minimum. So maxes and mins, we'll talk a lot about that over the next few days. And then, you know, just to put it in its most basic terms there, the minimum represents the lowest point on the graph. So again, you see that parabola, the low point right down there, that would be your vertex if the parabola opens up. If the parabola opens down, then the vertex obviously is the maximum. Okay, and I'll go ahead and highlight that piece right here, and or the highest point on the graph. So it's an absolute max or an absolute min, the low point or high point, and again, just based on what you see up there. So what we want to do is come up with a wave from standard form to go ahead and calculate that vertex here. Now, I'll leave this to your discretion. I'm going to go ahead and create my own quadratic function, as it says with this investigation right here, and then ask us to do a particular calculation based on that piece. And if you want to create a different one, you're more than welcome to, and do the calculation on that. So I'm going to go ahead and create a quadratic. I just have one on my paper here, so I might as well use that. So how about something along these lines right here? So 2x squared, how about minus 8x minus 3? So y in terms of x it is a polynomial of degree 2, and you have your ax squared, your plus bx, and your plus c. And so what we're going to do, is, as you can see on your paper, is a very particular calculation, this opposite of b over 2a, and potentially you've seen that before. And so I'm going to go ahead and do that just off to the side here and then put my answer right in there. Just one thing to notice, the numbers will get a little harder. That 2a kind of should be in parentheses right there. But for right now, I don't think that should hurt us in any way. Okay, so let's see what we have. Opposite of b, so here's my b value, which is -8. And so opposite of -8 is +8. And then down on the bottom again, I'll throw some parentheses in there, but basically 2 times 2. Okay, so 2 times, and then here's our a value right here. And so I just get 8 over 4, and there we go. It's just 2. So we did that calculation, opposite of b over 2a. Now here's how we're going to treat this. So once I get this number from this calculation right here, I'm going to treat that as the input to the function. We've talked a lot about inputs and outputs. So what I'm looking for then, in essence, as it says on your paper, substitute that number in for x and find the value of y. What I'm basically looking for in terms of function notation is f of 2. So 2 goes in for x, and what I'm looking for is the output value. And so if you get an opportunity here, if you want to keep it as y equals or f of 2 equals, but basically 2 is going to go in, and what I'm looking for is what comes out. So something like that should do. And let's see if I can kind of pull this off right here. We've got 2 times 2 squared, so that's going to be 8. Minus 8 times 2, so 16. And then minus 3. So just working left to right here, 8 minus 16 is -8. And -8 minus 3 is -11. So end up getting this piece right here. And you could hopefully confirm that. So we did this calculation and got what I would perceive as an x value. That goes in, and of course I end up getting the corresponding y value. All right, let's go to the next piece on your paper. And it says graph the function on the calculator and determine the vertex. All right, so let's pick up the calculator here, let it do some of the work for us. And I'm going to go to my y equals. If you could do the same, that would be great. I have a 2x squared, and then minus the 8x, and minus the 3. And when you can, just go ahead and hit zoom, and then number 6 there. And notice you get your nice looking parabola. It's opening up. Not the ideal window. We can change that if you'd like. But basically, you can kind of see where would that vertex be. And it looks like it would be an x value of 2. And I'm guessing there, just based on what I see, it looks like that y value would be down at -11. And so the vertex from the graph that we just looked at on the calculator is equal to the exact same ordered pair, 2 and then -11. Perfect. And this would work with any quadratic function. As I said, if you wanted to create your own and do exactly the calculation that we did, it works out the same. So graph the function on the calculator and determine the vertex. Let's go ahead and obviously put that as an ordered pair. And that's actually the key. Just what I've seen over the years is sometimes students will do the initial calculation and forget that a vertex is a point on the coordinate plane. So it has an x, it has a y. It has an input and an output. Okay, so let's conclude this one. So it says to determine the ordered pair of the vertex of a quadratic function in standard form, underline that for me if you would, it's going to look like this. So that calculation, and by the way, that should look somewhat familiar. I think we've seen at least a hint of that before, this opposite of b over 2a. Maybe we can make a connection further down on this notes worksheet too. But opposite of b over 2a should give us the input, and then in order to find the output, we basically find the function value at that number. So it would look something like that. So opposite of b over 2a, and then plug that back in to get the corresponding output value. Nice. You're going to be doing that a few times here today and kind of working with that piece. So again, keep that in mind. That is probably the most prominent of the 5 characteristics that we'll look at, I think, on this notes worksheet. All right, I'm going to move forward here. Let's get all of the characteristics taken care of. Then we'll go ahead and do a few examples to kind of back it up. So number 2, not too big of a deal, but just in terms of a graphical characteristic. is the axis of symmetry. And it says the axis of symmetry is a vertical line that passes through the vertex. I'll tell you what, just as we're kind of thinking about that there, I'm going to go back a screen and let's go ahead and sketch it in. You have it obviously on your paper there. So axis of symmetry, as you can see, is a vertical line. And I didn't draw this perfectly, but you can see essentially it divides it in half where half the graph is reflected over the other half there. And you can do the same thing here. So a lot of working in graphing with parabolas revolves around the concept of the symmetry over that line. So it's a vertical line of symmetry. Okay, well, let's see if we can model this one. So it does say on your paper what is the equation of the axis of symmetry. And this one's actually relatively fast if we can come up with a conclusion for it. So let's see if we can refresh memories here. First of all, it is a line on the coordinate plane, so I should be able to model that. In further detail, it is a vertical line on the coordinate plane. So I'm asking you, do you happen to remember how to model a vertical line on the coordinate plane? And if you remember correctly, it comes down to all the x values are the same. And so as a result, the way to model it is to have x equals a particular number. Well, here's what's kind of fascinating about this, and I'll go on back to my previous screen. If you notice the way I detailed this, all the x coordinates are the same on this particular line of symmetry, and let's go further, it goes through the vertex. So what conclusion can be drawn in terms of the equation? And if it goes through the vertex and it has the same x value as the vertex, then, hey guys, it has to be x is the opposite of b over 2a. Whatever that number is, now the vertical line is the axis of symmetry. Not too bad. And I'll just go ahead and quickly bring my calculator up here. As you can see, here's x equals 2 right there. And it divides that parabola right in half. Cool. All right, so not too bad. Again, once you find that vertex, then the axis of symmetry is very much a natural extension of that. No big deal there. All righty. Let's move forward here. What is the x-coordinate of the y-intercept? And I'm just going to go ahead and bring my coordinate plane up. Sorry, let me go ahead and clear that. So, you know, anywhere, if I'm on the y-axis for any function, as a matter of fact, what do we know about the x-coordinate right there? And if you can kind of take a look at it, whatever the ordered pair is of that y-intercept, the x-coordinate is going to be 0. And so think about that for just a second. It says for a quadratic function in standard form, then what would that make the y-intercept? If you know x is 0, and again, I'm just going to go back and forth with these screens. If you know that the x is 0, what does that mean in terms of the y-intercept? Well, if that's 0, that part goes away. If that's 0, that part goes away. And what are you left with? Just that constant on the back, the c value. And so this one's also a very quick one. In standard form there, it's just 0, comma c. And so I'm just kind of thinking of that last one right there. I guess I erased the graph on the calculator. But this one right here, without blinking, I could be pretty sure that the y-intercept is just going to be 0, negative 3. So you can see we've done 3 characteristics so far, and 2 of them are really, really quick. Nice. All right, so you talk a lot about intercepts when dealing with graphs here. So the y-intercept is definitely one, kind of the initial value. We'll talk about that when we do an application or two further down on this sheet. But let's get into the x-intercepts, kind of another one here. Do a lot of work around the x-intercepts. So it does say in your paper, what is the y-coordinate of the x-intercept? So again, I'm just going to bring my calculator up here. If you know this, great. So here's the x-axis, of course. The graph is going to cross or touch that x-axis. And what would be the y value on that x-axis? Well, no matter where I am, the y value, of course, is going to be 0. And so let's go ahead and put that in place. So in this case, in order to find the x-intercept, I substitute 0 in for y. And as you can see, what's great about these notes worksheets is it gets us going on that next piece right away. So what methods have we used to solve a quadratic equation of the form? And there it is, everyone. Look, now I'm putting 0 in place of y. And that should look very familiar. We've been able to kind of solve a lot of these equations using 4 distinct methods. So be curious to see if you remember each of the names of the four methods there. Well, I'll kind of go in order here. Number one, and probably the most time efficient, if it does, is to factor it. So factoring is one way to solve a quadratic. Break it down to its factors and set them to 0. One that doesn't come up very often, but is a nice one nonetheless, is to undo the square. So we can either factor, undo the square, completing the square. That's a great one right there. I'm going to do a lot of work around completing the square. In fact, you'll see this on the day 2. So that's great, completing the square. Or last but not least, when all else fails, and we have it stored on our calculator, which is kind of nice, the quadratic formula. So all of these ways would allow us to solve a quadratic equation of this form right here, which in essence gives us the x-intercepts of the function. So putting 0 in place of y is really the same thing as finding the x-intercepts of the quadratic function. Okay, one more piece here and then we'll continue on. What is the quadratic formula? And at this level should be pretty confident with this, should remember it. So opposite of b plus or minus b squared minus 4ac, all underneath that root, and then all of that over 2a. And just one thing to note on this, and then I promise I'll move forward, but make the connection there. Remember that vertex or you know, kind of that axis of symmetry? Do you see that opposite of b over 2a? That calculation I had you find the x value of the vertex? Well, notice it shows up as part of the quadratic formula, and obviously that's not a coincidence. And if you kind of take a look, again, I'll try to be fairly fast here. If I have sort of something like that, there's my coordinate plane, and here's my vertex right here. Here's the x value, right? And that's the opposite of b over 2a. That's this part of the quadratic formula. And then the other part, the plus or minus piece, the b squared minus 4ac over the 2a, basically tells us how far to go to the right to get one x-intercept, how far to go to the left to get the other x-intercept. Because they are equidistant, that's where this comes into play. And so the opposite of b over 2a is right in between the two x-intercepts, this one here and this one here. So again, that's just the connection between those two. And that's why that opposite of b over 2a works for the vertex of the quadratic function. Okay, very nice. Let's see if we can go get number 5 and then start our examples there. So number 5, quick investigation to think about the direction, up versus down. It says create several quadratic functions where a is positive and graph them on the calculator. All right, we will do exactly that. And then a little conclusion on that piece. So I don't know, why don't we do 2 or 3? I think that should suffice there. So get comfortable just typing it in. So just all I need is a positive positive a value. So a positive 2x squared, and then the rest of the way really doesn't matter. So I don't know, plus x minus 4. I'm just typing in stuff, first thing that comes to mind. And maybe get another one there, something like this. How about, I don't know, 0.4 x squared. As long as that a value is positive, good to go. I'll do a minus 3x. And how about a plus 1? Keeping the numbers nice and easy. I think that's fine there. We don't have to overplay this one by any means. So I'm going to go ahead and hit graph. And you get 2 parabolas right there. You know, we can talk about the width of the parabola. That actually comes from the a value as well. The larger the number, the more narrow that a value is. And we'll talk about that when we get into some of the other functions as well. But also in this case, the smaller the a value, the wider the parabola. But regardless, in terms of direction, everyone, if a is positive, as you can see, those parabolas open up. So let's write that. So the parabola opens up. Oops. Let me just catch that. Good. Which means, of course, please make the connection. If the parabola opens up, then that vertex is a minimum. So keep that in mind. Parabola opens up, vertex is a min. And I think you could probably foresee what's going to happen here, but let's go ahead and confirm. You know what? This would be good. it says create several quadratic functions where a is negative and graph them. What do you say we keep these exact functions right here, except let's change the positive to a negative. Let's just insert a negative here. So do you see that little insert right here on the second of the delete button? I'm going to hit second and delete. And let's go ahead and throw in a little negative. And so same thing here. I'm just going to do second and that, and let's just insert a little negative. So everything else is the exact same. What happens when I go ahead and just put a negative in front? Well, as you can see, now the parabola is open down. Just by changing that one little piece, you change the entire nature of the parabola. It goes from opening up to opening down. So let's put that in. The parabola opens down. Okay, good. So just 5 nice graphical characteristics dealing with parabolas here. Hopefully nothing too heavy. In fact, I would venture to guess that you've seen most, if not all of that before. Well, let's go ahead and just solidify some of those pieces with the 3 examples that you see on your paper here. And hopefully it's clicking for you. So I won't make you point plot or anything like that, but it is important to kind of make the connection between the equation of a quadratic function and the graph of a quadratic function. So we'll do that via the characteristics. And so I guess here's what I would have us put on our paper. Let's just do one would be, let's see, let's start it out with the direction. Let's do that first. Might as well do that. So let's do 1 is the direction, 2 vertex, 3 axis of symmetry, and you don't have to do it in this particular order by any means. I'm just kind of thinking out loud here, to be honest. And then 4 y-intercept, and then 5 x-intercepts, if there are any. We'll find out. So let's go for it. And actually, as a matter of fact, it would be great for you to pause the video for about 2 or 3 minutes and see if you can come up with all 5, algebraically kind of working through, and then come on back and see how you did. Again, that would be the ideal. Okay, well, I'm going to start it out here. Number 1, the direction definitely is opening up. So vertex is a minimum, no doubt about that. So opening up. Now that vertex, let's get started on that piece. So opposite of b over 2a. So opposite of -4 is 4 over 2 times 1 down on the bottom. Again, I put parentheses down there just in case. So 4 over 2 is 2. Nice. Now basically, again, I'll sort of go with this piece right here. What we're essentially looking for is f of 2. So once we do our opposite of b over 2a, please don't forget the true minimum is actually the y value, the output. This x value right here, this 2, is just what produces the minimum. So let's go ahead and figure that out. It's 2 squared minus 4 times 2, and then minus 12. And so when all is said and done here, I'm getting a 4 minus the 8 and minus the 12. I'm getting f of 2 equals -16. Hopefully that's the case. And so please don't forget that vertex, of course, as an ordered pair, is going to be 2, -16. All right, wonderful. Again, I would go ahead and just put a little asterisk next to that one. For all types of functions, you're going to have to pull off that piece. Number 3, axis of symmetry. This one shouldn't be too bad. We did all the work. Remember, vertical line going through the vertex. So it's just x equals whatever our opposite of b over 2a is. So in this case, x equals 2 divides that parabola nicely in half. Y-intercept, also quite fast here. You know, 0 goes in for x, and it's just a 0 goes in for x, it's the c value. So 0, -12 would do. And last but not least, those x-intercepts. Let's be clear on this, and remember all of this right here was to get the vertex. The other work I'll do on the board is just to go ahead and find the x-intercepts. And I kept this one really nice and straightforward for us. But basically it would be that piece right there. And so put in 0 for y and solve for x. And we should be experts at being able to pull off something like this. You know, I'm thinking that we could go ahead and try to factor that, at least give it a try there. And I'm seeing an x minus 6. How about an x plus 2? And that's looking pretty good. So as a result there, I'm seeing x equals 6, x equals -2. If you could get in the habit, please, of writing these x-intercepts as ordered pairs, that would be great. So don't write it as 6, -2, but let's write it as 6, 0, and -2, 0. I think that's a little better. Okay. Now, just one thing to note, not every parabola is going to have two x-intercepts. And you've probably seen this before, not that I'm going over it explicitly right here, but theoretically a parabola can have no x-intercepts, it can have one x-intercept, or it could have two x-intercepts. And if you can humor me for just a second, you don't have to write this on your paper, just kind of stare at your screen for 15 seconds. But, you know, I can just go ahead and, here's a parabola. Looks great on the coordinate plane, but it does not have any x-intercepts. And that would bear out right here. You just wouldn't be able to solve the equation in the real number system. There would be no real numbers that make that true. You could actually have one x-intercept. I missed it. Let's get closer and closer. There it is, kind of. But you get the idea. The vertex would be right on the x-intercept. Something like that. And then as we could see, this one right here really has two of them. So 3 different scenarios with a parabola and x-intercepts. Should just be aware of that piece. Okay. We'd love to just make sure all this makes sense here and it all fits in coherently before moving on to the next problem. So I'm going to go ahead and just do this. And so let's see what we ended up getting here. 2, -16 all the way down here. There was the vertex, axis of symmetry going right on through. I saw 0, -12 is the y-intercept, so something around there. And then an x-intercept at 6, 0, and -2, 0. And there would be our parabola, something like that right there. Oh, goodness. I'll try to draw a better one there. Yikes, I butchered it. Oh, well, you'll hopefully draw it better on yours. Should look quite a bit nicer than that. Just one thing to note, again, just kind of made that connection before. Remember that the x-coordinate of the vertex was +2, and there's 6 and there's -2. Again, here's that scenario. That opposite of b over 2a is equidistant from each of the two x-intercepts. So that's where that number comes from. It's right smack in the middle of the two. 4 units this way, 4 units that way. Kind of cool. Alrighty, I think I butchered that. I can't stare at that any longer. So I'm going to erase mine. You can hopefully keep yours. Alrighty, let's go get 2. There we go. So a little just nice application, still putting some stuff together with it. An object is projected vertically from the top of the building. Its height after t seconds is given by this function right here. So a relationship of 2 variable quantities, height and time, and the nature of the mathematical relationship is quadratic. And so what we have here with time values, those are our inputs. If I know the time values, these are the mathematical calculations that I would do in order to get the height values. So height in terms of time. And I believe height is in feet here and time is in seconds. So again, let's just go ahead and run through a few of these. Find the height after 1 second. That sounds fine by me. So this is a t value or an input. So in essence, everyone, I'm looking for h of 1. I hope we're all clear on that. Inputs versus outputs. It makes all the difference dealing with functions. In this case, 1 is an input, so it replaces the inputs, of course. And times 1, and plus the 100. So let's see what we end up getting in this particular case. I'm just kind of looking at this piece right here, 16, 144, and a 100. If you don't mind, you do the calculation there. I'm getting 228 on that. So I'm going to go ahead and put that off to the side. I hope I have that right there. So I have 228 when all said and done. And I'm going to go ahead and just, since we're talking units and a relationship there, I'll go ahead and put the feet on the end. So 1 second, 228 feet. And that's just kind of a filler question. It really, in reality, if I give you any input for any function, you should be able to come up with the output. Okay, now everybody, if you would, tie those together. B and C go together. And here's Here's the phrasing that you're going to see, and it's got to click right away. So when will the object reach its maximum height? And in letter C, what is the maximum height? So in a quadratic relationship, and the a value is negative, right? So everyone see that there? The a value is negative. It means this parabola is opening down. All the t's and h's that go together would form a parabola that opens down. And the maximum, if we're talking about maximizing it, is the vertex. And so off to the side, I would, without question, write the word vertex. So please make that mental connection if you would. Quadratic, a is negative, maximum, we're looking vertex. If it's quadratic and a is positive and we want a minimum, we're talking vertex. Okay, so how do we come up with the vertex? Well, very simply, we need the input first. In this case, it's not x, it's t. And it's the opposite of b over 2 times a. So I would ask you to do this calculation, but it should look something like that right there, give or take. Opposite of b over 2a. And so, again, I'm just a little careful with this, especially the calculator, how it interprets it. You're going to want that 2 times a in parentheses. So I can probably do a little mental arithmetic here. I've got the negative 144 over negative 32. Ooh, I'm seeing 4.5 on that. So 4.5 seconds, it looks like. When will the object reach its maximum height? That is the input that is going to produce the maximum. So 4.5 seconds. Now, how do I actually get the maximum height? Well, again, it's a relationship between h and t, and I have t. And so I have the t that's going to go ahead and maximize this. So let's find out what it is. So now I just need the height at 4.5 seconds. That's the key with the vertex, everyone. Remember, it's opposite of b over 2a, and then you plug it back in. So negative 16 times 4.5 squared, 144 times 4.5, plus the 100. And so when all is said and done there, I'm going to actually calculate this one just to make sure. So here's what I have. Negative 16 times 4.5 squared, and then plus 144 times 4.5 plus the 100. There we go. We've got our winner. So this object will reach a maximum height of 424 feet. Okay, good. I'm going to box a few of these answers up, just kind of looking at them here. That looks great, that looks great, and that looks great. Outstanding. Okay, good. A couple of the other characteristics, at least just trying to provide a little context for them. So what is the y-intercept here? Hey, keep it nice and simple. Y-intercept is just this value right on the back. So the y-intercept would be 0, 100. And what is that 100? So if you kind of look, it says an object is projected vertically from the top of the building. Its height is given by that right here. So it looks like time is 0, height is 100. So y-intercept always, always, always represents the initial value of the dependent variable. In this case, the height is the dependent variable. So I'm just going to write initial height of the object. But let me state that again. A y-intercept really is always just the initial value of the dependent variable. In this case, just the initial height. Nice. Determine the x-intercepts. Sounds great. So let's go ahead and get this piece. X-intercepts, let's see if we're getting into a rhythm with this. As soon as you see what's going on, x-intercepts there, 0 goes in place of y. So that's the key. Now, this one doesn't quite look as pleasant as the one I gave you in example 1, right? I will tell you up front that does not factor, just FYI. You can't undo the square, that's not good. And quite frankly, I don't want to go through the motions of completing the square right there. That doesn't look pleasant at all. So you know what, why don't we use that quadratic formula program? It's a good application. We've got some pretty heavy-duty numbers there. Why not let some of the technology do some of the work? So I am hoping you remember how to pull this off. You do have the quadratic formula program on your calculator there. I'm going to go ahead and bring mine up. So there we go, quad form. I'm going to go ahead and hit enter on that and hit enter one more time. And remember, as long as it is set to 0, and that's just what it happened to be, x-intercept is when the y value is set to 0, it's ready to go. Oops, I typed it in wrong. That would help if I got that right. So A is negative 16, B I think I saw is 144, and C is the 100. And again, let's make sure I get that right. Okay, enter that in if you get a chance, and I end up getting 2 values there. So about negative 6.648 and about 9.648, give or take there. Excellent. Let's write them as ordered pairs, and then we'll kind of talk about what that represents. So I think I saw, if memory serves, about negative 0.648, comma 0. And then I also saw 9.648, comma 0. All right, 2 x-intercepts, or t-intercepts for lack of a better description. And what do they represent? Well, it's funny, I sort of went singular in the way I phrased it, and there is a reason for that, of course. I would argue only one of these makes sense within the context of the problem, because they're t-values, right? A negative t-value just doesn't make a whole lot of sense here. So even though it's a good one, it is an x-intercept, you know, we're not going to use it. So what's the 9.648 represent? And I guess we would argue that it's when the height is 0, right? Because that's exactly what we put in. The dependent variable is 0, so it's the time it takes for the height to be 0. I'm going to write it pretty much like that. So the time it takes, if you want to paraphrase, you're more than welcome to. Time it takes for the height to equal 0. Or really, it's the time it takes for the object to hit the ground, to be honest. But, you know, as I said, paraphrase however you'd like. So the time it takes for the height to equal 0, or really the time it takes for the object to hit the ground. That's probably even better. Okay, letter F, just sketch a graph of the function and label the key characteristics. Why don't we go ahead and wrap this up relatively fast here. So we don't have to go ahead and graph it on the calculator. Let me just kind of sketch out what it would look like, and hopefully all of that comes together nicely. So it should look something like this, just from the information that I saw from above. So a couple things to note. There's your y-intercept. Object starts 100 feet above the ground. It reaches a maximum height 4.5 seconds later at 424 feet. And then it comes on down and hits the ground at about 9.648 seconds later. By the way, here's the other x-intercept, which is, might as well put that in, negative 0.648, comma 0 also. So you can kind of see all those pieces come together. Nice. Looks really nice. Okay. Well, let's do just the one more. Kind of doing nicely on the time. Should be comfortable at this stage to be able to work through a set of data and to be able to model it on the calculator. And this happens to be a great application to do it. So example 3. A study was done to compare speed in miles per hour with mileage in miles per gallon. So essentially, fuel efficiency of the car in terms of how fast the car is driven. So fuel efficiency is the dependent, and the speed of the car is the independent. Fuel efficiency depends on how fast you drive. So it says the results are shown. So X represents, again, how fast we're driving, 15 miles an hour, 20 miles an hour, et cetera, et cetera. And this was the recorded fuel efficiency of the car. So at 15 miles per hour, it gets 22.3 miles per gallon. It starts to increase. The faster we drive, the more fuel efficient it is. Again, just kind of data points along the way here. And then as you can see, it starts to go down after a while. So the faster you drive, well, then the engine starts to have to work harder, and the less efficient the car is. So what we're going to do is find a quadratic regression for the data and kind of go from there. So if it's been a little while since you've done these, here's how I would always characterize it. It's really a 3-step process. It's enter the data, view the data, and model the data. And again, at this stage of your mathematical careers, should be fairly comfortable working with this technology. So a couple preliminary steps to get it going. If you would go to the y equals and clear it out. And I'm going to go up and just turn my stat plot 1 on at this stage. So you can do that as well. Just highlight plot 1 and hit enter. And so that's on at this point. If I'm not using it, I would go up there and turn it off. So maybe after this scatter plot, you would turn it off as well. But make sure it's on for right now. Okay, now 3 steps, as I said. Enter, view, model. So let's enter. Guys, it's the Stat button on your calculator. So you hit Stat and Edit, and you should get something like this right here. If you have some data in, the easiest way to do it is just to go up to the L1, just like I did right there, and hit the Clear button on your calculator, and then the Enter button on the calculator. And that should clear anything out. If you have anything in the L2, go up and do the same thing. So go up, hit Clear, and then Enter. All right. Now, I'm sure you are quite a bit faster at typing than I am, but I'll see what I can do here. So X's are the speeds, going up by 5s. So everyone take a moment, get those in for me. I will try to get this as quickly as I can. I am very slow with typing this in, especially working on my board here. It's not conducive to going fast anyway. Okay, one more for me. Good. Now go over and let's match them up perfectly. If it doesn't match up perfectly, the calculator will let you know. So let's go ahead and type in these. And be careful, I've seen so many typos over the years, and obviously one little misstep, it's going to throw the entire regression off. So your set of data has to be perfect here, entered in. So different data points recorded here. Obviously there could be margin of error for individual points. You kind of see it go up and down right in here and then up again. But the bottom line is these are just data points, and what we're trying to do is come up with an overall description of the pattern for these data points. And that's what we're going to do here in just a sec, if I can ever do this a little faster. Okay. Getting close. All right. Phew. I'm sweating from this one. All right, now here we go. Entered. X's and Y's all matched up perfectly. See it. So everyone hit zoom at the top. And you can hit number 9 if you'd like, but it's what's called the stat window. So zoom stat right there. I'm just going to hit number 9, and there we have it. And if you kind of take a look at the graphical pattern that emerges with these data points, it has that real good parabolic feel, doesn't it? Kind of up and then down, some good symmetry in there. I mean, I think a quadratic model is a really nice fit for that set of data. And so that's the conclusion that we would draw at this stage. And now we're going to let the calculator come up with the precise model for it. So enter, then view it, and we interpreted when we viewed it, and now it's time to model. So I go to stat, I move it over 1 to the right, and I go calc. And we probably have seen linear regressions before at this stage, but now it's time to do a quadratic regression. So number 5. Now I'm going to do something in addition to this. If you want to, you can. This is kind of optional at this point. I like pasting the model into the y equals so you can see the graph in relation to the data points, but you don't have to. If you want, you can hit enter at this stage and go forward. But I'm going to hit the vars button. I'm going to move it over 1 to the right for the y. This is a function. And what I'm going to do is put the regression into the y1. So I'm going to hit enter. Now I hit enter again, and there we go, guys. Take a look. There's our great quadratic model. I'm going to go 3 decimal places out. Here's our A, here's our B, and here's our C. Whew. All right, so let's go y equals. And I think I saw this, and I should have it on my paper here. So negative 0.008x squared, that was the A value, The b value is 0.746, so that's the b in front of the x, and then the constant on the back is 13,469. Notice the a value is negative, so we have a parabola opening down, and that's outstanding. Given a speed, here are the mathematical calculations to come up with the fuel efficiency. One last piece, everybody. It says determine the speed for which the miles per gallon is greatest. Here's the key right here, everyone. Notice it's a parabola opening down because the a value is negative. We're going to maximize the fuel efficiency, maximize the dependent variable. And so long story short here, guys, it's the vertex. If I did the opposite of b over 2a algebraically and then plugged it back in, would I get it? Yes, indeed. Do I want to do that? I'm going to let the calculator do some work for me. So watch what happens. You can sort of watch here and sort of see this in action, but that would be the overall parabola, best modeling that set of data. And notice, there it is right in there. How fast should we drive in order to maximize the fuel efficiency? Again, if you do the opposite of b over 2a and plug it in, that's fine. But I'm going to do a maximum right there, so number 4. And unfortunately, it puts me pretty close. So if you remember doing this before, you come just a little bit to the left of what would be the maximum, hit enter, a little bit to the right, hit enter one more time. And there it is. There's the speed. There's the best fuel efficiency for this model of car. Let's get that in and wrap this up. So I got 45.5 miles per hour, and I got 30.4 miles per gallon. Oh, that's great. Okay, so good set of data there, everyone. I'm going to wrap it up at this point because it was a rather long one, but I should be comfortable kind of working with the set of data, coming up with a quadratic, and working with it. Again, just real quick, if I did opposite of b over 2a, guess what I would get? And if I plug that back in for x, guess what I would get? Hopefully that's clicking. All right, guys, I'll wrap it up. Thanks for listening, of course. Let me know if you have questions, and practice. See if you can pull it off.